to confirm some license or confirm some agreement that you agree that with the fact that the video is recording, and it could happen that, for example, your nickname or your avatar or whatever can be recorded in the video, which is pretty normal. Yeah, you know, from COVID times, I think it's pretty normal. Okay, so let's start. I hope that you can see my share screen at this moment. So this lecture will be dedicated to biomedical statistics, but very gentle, very brief introduction to biomedical statistics, because biomedical statistics is something which is pretty complex. It's a kind of science somewhere in between the biomedicine, and statistics. So it usually use some of data of some biomedical provenience and apply some various methods from statistics or from data analysis and so on, just to, for example, try to test some hypothesis or just describe the data for different, for example, levels. It could be described using some numbers, some plots, some graphical visualizations, and so on and so on. So we are just going to talk about this. I'll try to do it in time. So we have something like 1.5 hours. So I'll do my best to do it in this time. So my name is B81180. I'm just an assistant lecturer at the Department of Biomedical Statistics here at our Institute of Biophysics and Informatics for Faculty of Medicine. And also I'm just assistant lecturer at the Department of Statistics and Probability of Faculty of Informatics and Statistics, which is also a different university here in Prague. So I do statistics both on these departments. And I started my career as an oncologist. So I studied medicine. I graduated medicine in 2013 and did annual oncology for 1.5 year. And then I just, let's say, realized that I just realized that it wasn't like a career for me. So I rather switched to statistics to do some more quantitative like things, because this way of thinking is pretty more. I'm just more familiar with this way of thinking. So that's maybe why that I'm for today, like here to talk with you about statistics, because I did both the medicine and now I'm just doing statistics. So that's why maybe I'm here to give you this kind of talk. Okay, so let's start. So what you can see now is just a kind of colophone. Don't be scary about this. It just means that since it is going to be online, I'm also going to provide you with my slides, of course, but it's going to be online, both in video and also the slides as PDF, for example. Definitely should be something like colon. So you are feel free just to use the slides once I'm just going to provide you with them. And what you should follow is just a CC license, Creative Commons license. It's like some kind of copyright license. Maybe you know there are some kind of copyright licenses for example, some kind of properties, like own properties, like for example some music and so videos and so on. But of course this is like a study material, so I are used for copyleft license, which means that you can definitely share it if you want to. What you should do is, once you are willing to share it, is to use the same affiliation and maybe my names, just to because this is just to because I'm not like owner of my slides. Our department is the owner of my slides. NC stands for no commercials. So I hardly believe that someone is willing to buy the slides from you. But just in case that it could happen, don't do it. Don't sell the slides. No commercial derivates are like allowed to be done. And ND stands for no derivatives. It means that, for example, we can print the slides out. Definitely you can make some notes, and of course you can do everything this once I'm going to provide you with the slides. But no derivatives means that once you do some kind of derivations, like some footnotes, notes, marginal notes, or whatever kind of remixing of this document, in such a case, you are not allowed to spread it, like, let's say, outside of walls of faculty, because of the fact that our department can guarantee a level of quality or level of, let's say, level of information, pieces of information which are in the slides are true, only without the derivatives. And this is like kind of colophon. You know that we live in the times of disclaimers. So this was like my disclaimer, which I have to start with before the lecture itself. Okay. So let's look at the intended outline of my lecture. So we are going to start with a quick introduction. There will be some very basic terms and some motivation, under motivation. Then I will start with some basic terms which are, for example, important for, let's say, some basic orientation in the topics of biostatistics. Then I also will move to descriptive statistics, which is something which I suppose to be relatively important for you and important for students of both medicine or dental medicine, because of the fact that for example, someone of you will just, let's say, continue after the undergraduate studies to some kind of postgraduate studies or graduate studies like PhD studies. And definitely, if we are just willing to do this, you'll have to face with some research or research, and you are about to, let's say, write some papers. And definitely, you are about to, in such a case, you will be forced to do some science, let's say science in quotations, like a research, biomedical research. And definitely, some publications are expected to be right using about around this around your future research, and you have to use some statistics. And main like the main point of the statistics will be statistics, because the more, let's say, advanced statistics can be, for example, done by some statistician. You can, for example, ask some statistician just to do the statistics for you. But some very basic statistics, like descriptive one or some basic plots, this is something which is which can be pretty useful for you to be skilled in it. So I'm going to talk about this a bit more. And the last part of this talk, I will talk about inferential statistics, which is a bit more complex topic. But to be honest, this is like the inferential statistics, like the this is just a, let's say, grow of all statistics, because this is a kind of statistics which is able just to, for example, test the hypothesis or do some inference, to do some predictions, and all the buzzwords you could, for example, already heard about in a talk or in the lecture about artificial intelligence and so on. So this is because artificial intelligence and machine learning are pretty close to inferential statistics. Yeah, these honestly, I would also may also say that inferential statistics is something which is, for example, like an ancestor of machine learning or artificial intelligence. So statistics was before like the machine learning or artificial intelligence, because some of the main concepts of inferential statistics are the same concepts what machine learning or artificial intelligence in medicine also use. Yeah, and that's it. So let's start. So what is the motivation? I would say that maybe definitely, you know, when there's something like evidence-based medicine, this is also what we are going to talk about for the next time. But medicine nowadays, for example, for the last maybe 50 or 60 years, is usually based on some evidence. And to be very honest, evidence in medicine means that the evidence is statistics. It means that if there is some statistic, is there some evidence? It means that it's a statistical evidence. It means that, for example, if we have some initial idea that, for example, some let's say some there's some etiology of some let's say illness, in such a etiology of some diagnosis, we have to collect, let's say enough data, sufficient amount of data to be, let's say, sufficiently confident that we are true, that we think that okay, the etiology of some diagnosis could be something. Okay. So the evidence in medicine is just a statistic. This means that we have to collect enough patients to be sure, to be pretty sure that something works in some way. So in evidence, statistical evidence means evidence-based medicine. There's nothing more than just simple statistical evidence. So the more patients which are, let's say, for example, in agreement with our prior hypothesis, then it means that we can be more confident about, for example, about our hypothesis. It works like this. So evidence-based is nothing more than only collecting enough data, collecting enough patients, and collecting enough yeah, knowledge which is in agreement with our prior hypothesis, and that's it. So it's like a kind of different point of view on evidence-based medicine, but from the point of view of statistician, definitely this works. You know that there are plenty of medical data which are collected on a daily basis in medicine, and this is also a point of nowadays, because we know that, for example, the amount of all the data which are collected on a daily basis, it's so large, like the amount is so large that, for example, the whole power of all computers all around the world is not possible just to analyze them in real time, on the fly. It's simply not possible. So nowadays, just the let's say the production of all data is much more larger than our computer power to analyze them. So it means that there has to be something like a science or some kind of, let's say science kind of field, kind of area, which is about to let's say more smart thinking about data analysis, and what statistics is about. Yeah. So yeah, we need something like statistics. We need something like data analysis, because the whole amount of data is much more larger than as I told you, than the overall computer power of all computers all around the world. So we have to like how to prove this is pretty simple, because you know that there's something like genetics and genetic data, molecular data. You know that all the combinations of all the genes, all the LLRs and so on, in comparison, for example, some proteogenomics and so on. These numbers are so high that they are much more higher than, for example, all gigabytes of RAM of all our computers we are provided by, for example. Also, what is a way or motivation to know something about this is that medical record thing is probabilistic. What does it mean? It means that if we have, if we, for example, try to diagnose a patient from some diagnosis, and we know that, for example, there is one very likely diagnosis the patient suffers from, then we start to work with the let's say idea that this diagnosis is the true diagnosis, and we are starting to treat the patient as he or she has this diagnosis. So this is a probabilistic way of thinking. It means that definitely, you know, that medicine is so complex that just at a given time point, a patient could have honestly many diagnoses. But at a given time point, we have to decide which one is the most important, and we have to treat the patient as he or she has exactly and only this one diagnosis. So this is a probabilistic way of thinking. Also, you know that the last of my three talks will be about some decision making in medicine, and we are going to talk about this in more detail. I think that this topic is relatively interesting. I hope so. Yeah. So it will be after 2 weeks. Yeah, there will be my lecture on a medical way of thinking, a medical decision making, and I think that this could be really helpful for example, your future practice. It will be more about some practical applications and some practical cases, practical examples, and so on. So some very fundamental level knowledge of statistics may be let's say even both interesting, I hope interesting, but also important for a student of medicine, regardless of general medicine or dental medicine. But you know, maybe sometimes we are in a third grade, so definitely some of your professors told you, for example, that some very up to date, for example, piece of information, for example, about COVID-19 or something like this. They are in some very current scientific papers, and the scientific papers are written in a language of science, and language of science which is more empirical, and medicine or biomedicine is a kind of empirical science, because there's no way of derivation like in mathematics, for example. So this kind of empirical and biological sciences use language which is in fact the language of statistics. Also, if you as I told you, someone who, for example, just think about his or her future career, that it could be, for example, PhD study. In such a case, since in such a case, we will definitely need to do some research and do some statistics in our papers. It could happen that some of the statistics will be, let's say, beyond your skills, which is absolutely normal. That in such a case, you have to communicate with the statistician to do the statistics in more appropriate way. But just to be able to understand the statistician and to communicate with him, with her, is definitely better to know some basic terms, which we are going to talk about for today. Yeah. So this was for motivation. Maybe the last piece of motivation, but I'm going to talk about more in, let's say, in 2 weeks. This is making the lecture. But maybe you know that if you try to open, for example, like the newest volumes of, for example, internal medicines from some Western provenience of, you know, that there are some like 1,000 pages of textbooks of internal medicines and so on. If you try to look at the list of abbreviations in these books, there are plenty of abbreviations, and some of them, I guess, for example, 10% of them are not from medicine or not from internal medicine, but they are rather from statistics or from some kind of science, like for example confidence intervals or for example relative risk or odds ratios or let's say p-values and so on and so on. And these terms are from statistics because the very cutting edge textbooks are written also in a language of science, as I told you, a language of science is in fact statistics. Okay, so this was for motivation. So it could happen, for example, like in the last year when we are going to study for your final exams, and you have, for example, to open this very modern textbooks, for example, from internal medicine, for surgeries, and so on. It could happen that some of them are written in a specific language, not only too much in the medicine, but also using some special idioms like p-values, where the p-values were lower than 5% and so on and so on, which is inspired in statistics, in fact. Okay, so I'm going to talk about two parts of statistics, two fields in statistics. So one of them is descriptive statistics, and the second one is inferential statistics. So descriptive statistics is something which I think that could be really helpful for you to know something about it, because as I told you, it could be relatively handy for you, for example, to be able just to make a, let's say, appropriate plot or calculate appropriate descriptive characteristics and so on. So descriptive statistics is just to take some simple data and try to evaluate or estimate some parameters, do some visualizations, just to get some get more into the data. So it's just to just to try to transfer them to some other numbers. So once you collect some data, it means that you collect some vectors of data, vectors of numbers, for example, or some other values, and you have to calculate some characteristics like arithmetic means or some characteristic of variability and so on, and do some appropriate plots, visualizations. This is something which is not so, let's say, so complex, and definitely I think that it's relatively, it's not so hard, it's not so difficult to do this kind of analysis, because it's just about the description of data. So this is something which I'm going to talk about in let's say 10 minutes. And the second part, which is maybe more important for a professional statistician, like a statistician by training, is the inferential one, which is like turning of some basic data to it works. It sounds like a buzzword, yeah, turning data into knowledge. But if for example try to search for Twitter for some analytics startups and so on, some tech startups and so on, many of them try to use this kind of like formula that we are turning your data into your knowledge, or something like this, turning your data into knowledge. This is like idiomatic buzzword, which is many times applied in a area of technological startups and so on. Because yeah, it's pretty, I would say it's pretty sexy just to have some data, to be able to collect data and turning them into knowledge. It means that even more sexy is just the turning data into predictions, because all of the players which are available on some like stock markets and so on, they are interested in predictions. Yeah, and this is also important in medicine, because making predictions means, for example, that you are able to say in advance that, for example, okay, my patient is going to develop, for example, Parkinson's disease in 5 years. If you are able to do this kind of prediction, and this is possible to do it, you can, for example, do some balancing just a kind of balancing plane or some other kind of diagnostic tools. If you are able to do this prediction, and okay, it could be pretty hard to, for your patient once you are going to tell her that you know that in 5 years he or she is going to develop this kind of disease, because it's a serious disease. But there's also a good piece of news about this, let's say, bad news. And the good piece of news is that if you are able to know it 5 years before its manifestation, you can, for example, start to apply the drugs for a patient, for example, in advance, to do some nootropics or some cognitive drugs and so on. And by doing this, you can, for example, slow down the developing of the, or for example, you can, for example, yeah, slow down the developing, for example, or something like that. So you can do something which is better for the patient. So also the predictions in medicine is pretty important. And also some generalization. It means that, for example, okay, I collect some data, for example, about 5 patients or 10 patients, which is not so many, but still something, some piece of information, let's say. And okay, by some approaches, by some heuristics, I'm able to generalize uh, the piece of information or generate some piece of knowledge I got about my 5 patients, and I'm able, for example, generalize them about or about all population or through larger distances, for example, to all population of my which patients of who have exactly the same diagnosis, for example. So generalization is something which doesn't sound so attractive like the prediction, yeah, but it's also important. Typically, for example, in genetics, when you notice there are some studies like casuistics or case series that we have, for example, with 1 or 2 or 3 patients, and definitely if you are able to do some generalizations to whole population of such a patient is definitely worth to be done. Also, what is typical for inferential statistics is that we can do the conclusion on some given level of confidence. So it means that, for example, okay, I am, for example, 95% sure that this works like this. Something, or for example, I am 95% sure that the population average of overall population average of body height is equal to this. Or we can simply conclude up that there is some given level of confidence by which on which we usually work in statistics, and this is also important for us because if we are, for example, more or less confident about something, it's far more closer to a real science than only, for example, saying, okay, one of my patients, for example, with COVID, I don't know, for example, has some special kind of symptoms. It means that all patients with COVID should have exactly the same, let's say, kind of symptoms. This is absolutely, you know, that this is absolutely nonsense. If you have one patient with some kind of exotic symptoms, absolutely not possible to generalize it to the whole population of patients. Yeah. So this is typical for this research. We have no way how to estimate the level of confidence. But on the other hand, in inference statistics, this is possible, and this is also not only possible, this is absolutely necessary to do it. So what is the, let's say, this is something like a, you know, that there's something like a central dogma in biology, that there's some DNA and there are some proteins like which are translated using DNA in a nucleus of cells and so on. So like as a parallel to this, there is something like a real or kind of dogma, central dogma of statistics in comparison to central dogma in biology. So this is a kind of flow chart, let's say, or kind of schema which describes how it works. Definitely, we live in a real world, and this or nowadays, real world produces tons of data because we live like in a data ages. Yeah? And real world produces tons of data, and descriptive statistics is something which collects the data and describes the data. And if the data are appropriately collected and described by descriptive statistics, then we have possibility just to apply inferential statistics to, for example, so try to extract some more interesting results, to do some conclusions, to extract, for example, some pieces of knowledge, like general knowledge or generalization knowledge, which could be applied back to our back to the real world we live in, and, for example, to get some better knowledge about the world we live in. Yeah, that's definitely a way of thinking, a way of let's say doing investigation in a science, like to collecting some data and doing some conclusions and extracting the knowledge, pieces of knowledge, just to and apply it back to a real world to know some better detail about our real world we live in, and also to do some, for example, prediction. This is maybe the most tricky part, the most tricky and most attractive part of inferential statistics. To do some predictions, about what not like what is the real world we live in, how it works, for example, but how it will work, for example, in 1 week or something like this. So it could be, for example, in some parts of let's say human activities could be pretty interesting, and also, for example, yeah, pretty interesting to know about what will be the near future. So it's all about doing the predictions. Okay, so now I'm just going to talk about the very basic terms, which is good to know about. So the first term is statistical variable. Statistical variable means that, or also statistical characteristics, or sometimes it's also called like a statistical metrics or parameters sometimes. But I would rather say only a statistical variable, which is maybe the most appropriate term. So what does it mean? It's just kind of quantity which is either a measurable or detectable by some, for example, instrument or in some other way. But it's a quantity of our interest, and all observations we collected, for example, so far, should have their values of such a variable. So let's say to say some examples. You can see that, for example, a typical statistical variable could be, for example, a body height or just a sex, like a female or male, or for the blood pressure, which is like measured in some millimeters of, or some indoors, yeah, rather, wage, which is, for example, in dollars or Czech crowns or whatever. Body height, I forgot to tell it, but it's, for example, centimeters or a meter, and so on. So whatever is important for us, whatever is in our interest, and could be measurable somehow or detectable some other way. It could be a statistical variable or statistical quantity. We also say just statistical quantity sometimes. So whatever you want, and in medicine, typically body height, body weight, blood pressure, or glycemia, for example, whatever you want, everything got it could be a statistical variable. Another term is statistical observation. Observation is just and some kind of atomic element of our interest, or we can also call it like a statistical unit. Yeah. So it's like, for example, I would maybe rather start with an example to make it maybe clearer. It would be, for example, student. Student definitely has its own body height, body weight, also some blood pressure, and so on, so glycemia, and so on. A patient, the same. Yeah. A country, for example, country can something like an average wage, something like this, or something like a cumulative let's say proportion of COVID positive or whatever. Yeah, this could also be a statistical variable. A molecule could have its molecular weight or something like this, or some kind of size, molecule size, and so on. So it's like a statistical observation or statistical unit. It's like an atomic element or atomic subject. Sometimes, if we know that we are in biostatistics and we measure like for example, some human beings or patients, and all, we can call it like individuals. Yeah. It's typical that we call it statistical individuals, or in abbreviation or for brevity, like individuals, because if we know that we are just simply measuring something which is like a either a patient or student or something like this, typically in biostatistics. Yeah, so those atomic elements, those subjects or those individuals, all of them, each of them should have its own value of our statistical variable of our interest. And the last term, which is important, is statistical sample. It's pretty easy if we know what is like a statistical unit or statistical observation. Then, in such a case, it's relatively easy to understand what is the statistical sample. It's just about creating a set, building a set of all the statistical observations or others, and this is the statistical sample. Or also, it's sometimes called like data or set or data set. Yeah, whatever variations of this word is possible. So it could be a class of students, a cohort of patients, and so on and so on. So these three terms are, I would say, important to know about. Maybe for your future, if you are about to start, for example, PhD study, do some science, do some research, and also in the near future, I will need something like a test, something like credit test at the very end of this course. So yeah, this is like this will be a typical question, yeah. Then there's I would say that a straightforward relationship between the statistical variable, statistical observation or unit, and statistical sample. So we can imagine that each statistical observation is a part of statistical sample, and it should have, as a part of statistical, it should have a value, its own value of statistical variable. Sometimes there is just footnote. Sometimes could happen that the value is missing from some reason or another. it could happen. Yeah, you know that since we live in a real world, and typically, even more typically in medicine, you know that, for example, for some patients, we are not able to get some values uh, of some variables. For example, if we have something like, for example, considering we have, for example, some patients which are, let's say, for example, they are, for example, not mentally able to be, for example, to undergo some kind of, let's say, uh, diagnostic tests or something like this. Definitely, from this reason, we are not able to collect the data, like a result of this diagnostic tests. Yeah. If, for example, they are like some loss of consciousness or something like this, yeah, the patient. So that this could be from this reason or from many other reasons. Sometimes it simply happen that some of the values are missing because we are able to collect them. So as an example, if we have a school class which is full of some students or pupils, we measure the body height of each student in this class. So the school class is statistical sample. Students are statistical observations or statistical units, or in such a case, I would maybe prefer to use like a statistical individuals, simple individuals, yeah, because we know that they're like they are from province of biostatistics, so they are just like human beings. And the body height is a statistical variable. This is what we measured. Yeah. So this is a statistical variable. So it's as easy as this. There shouldn't be a problem about this. I think it's a relatively easy concept. So quick intermezzo. Let's try to imagine that we are measuring a body height in a cohort of diabetic patients on a given ward, and we are about to identify what is in this case a statistical variable, a statistical observation, a statistical sample. I think it's pretty similar to the previous case with the school class and measuring of yeah, body height there. So yeah, this is actually I just wanted to write the body weight, but it doesn't matter. So rather similar situation. So a statistical variable. Statistical variable is something we measure. We can measure. So it's a body height. Yeah. Statistical observation, since this is a cohort of diabetic patients, so statistical observations are statistical individuals in such a case. So it's each one of diabetic patients. Yeah. So the first one, the second one, till the last one, diabetic patient, uh, all of them are statistical individuals or statistical observations. And statistical sample, this is just a cohort of all of them together. So it's just a cohort of diabetic patients or a set of diabetic patients or a group of diabetic patients. And maybe a question which is related to this task is what is on a given word? It could be, for example, bed word. It could be, for example, it could be not related to the task. To be honest, if we are talking about statistical sample, it's better to tell it it's just a cohort of diabetic patients on a given ward. Yeah. Like it's maybe more in detail, it's more specific. So to be more exact, a statistical sample is not only a cohort of diabetic patients, but I would rather say it's just a cohort of diabetic patients on a given bed ward. Yeah, this is a full description of a given statistical sample. So including the on a given ward. Yeah, let's say something like this. Okay, so now we are moving towards the descriptive statistics, and as I already told you, it's just about to describe data or just describe the statistical sample because usually we are able to collect only a limited sample. It's pretty rare to be able to collect all the population. I'm going to talk about what is the difference between the statistical sample and statistical population a bit later, but what we are able to collect is just a statistical sample. So for example, a sample of 10 patients or 5 patients, maybe 100 patients. If you are lucky, for example, 500 patients or 1,000 patients. Maybe you read some of our, for example, nowadays studies in COVID-19 problematics. The teams, like scientific teams, are able to collect data about, for example, 40,000 of patients. Yeah. But maybe also know about there was some like a fear about the faked data, fake COVID data. It was related to some some US universities that some of the data were pretty dummy, they were just faked. Yeah. So yeah, it could also happen that if there are some unbelievably high statistical samples, it's good to to ask ourselves just if it is possible to collect so many data, so many patients. So there was just an affair last year. It was like an affair about faked sample of 40,000 of COVID patients. All of the patients were simply, it was just simply faked. Yeah, they were non-existing people. Okay. So how to describe statistics? How to do the statistics? So how to describe data? Usually, we can use some numbers, some specific numbers. We usually call them characteristics or parameters or some kind of. Or sometimes it's also called statistics. But I didn't want to use this term because it could be kind of misleading or kind of confusing. All of them is about statistics, but some important. So some important characteristics are also called statistics, but I understand that it could be a bit confusing for you. Or parameters, for example. They could be formatted in table if needed. Yeah. And also the second approach, which is definitely worth to be mentioned, is a graphical approach. I'm going to talk about both of them. And the numerical characteristics and graphical approaches may definitely differ, which depends on the fact if we are talking about a quantitative statistical variable or qualitative. So quantitative is I'm going to talk about it in the next slide, but quantitative is the one who is related who is represented by numbers, and the numbers are meaningful, for example, to do some calculations using them. And qualitative one, so for example, quantitative statistical variable could be, for example, blood pressure or body height or body weight. Definitely have two body heights. You can subtract them to calculate the difference between them. Yeah, it's pretty meaningful. On the other hand, a qualitative statistical variable is a kind of variable where this is typically not represented by numbers, but it's typically represented by some categories. It could such a typical variable is, for example, gender or sex. For example, if you have considering there are only two like genders, like females and males. So if you have a sample of some patients and we are about to label them by females or males, each one will be either a male or female. I'm sorry for this, first binary understanding of a word, but still, in medicine, still we usually use, like for sex, we usually use only female or male labeling, because there is a kind of different concept between gender and sex. Gender is something like more about psychology, about how the individual like consider themselves, what is closer to, like it feels themselves rather as a female or male. But the sex is more about the biology, so more about the biological identification, and you know how it works, how it works in anatomy and so on. So that's for example, typically qualitative statistical in medicine could be sex, like male or female, or for example, tumor grading. It's 1, 2, 3, or 4, or tumor staging also 1, 2, 3, or 4, and so on, or some kind of different scales which are typical for medicine. There are plenty, or like dozens of scales, clinically based scales, for some severity of pain here, or some severity of some, for example, for description of mental state, and so on and so on. Definitely, you also know some of the scales typical for example, dental medicine. So yeah, these are typically qualitative because they are not represented by numbers. And if they are not represented by numbers, it's not possible to calculate some summation of them or subtraction of them. So we are going to use a bit different numerical characteristics than we can use for quantitative ones. So to be more specific, a quantitative statistical variable is usually described by numbers. They could be real or integer. And also, very often, they also got its own unit. So as an example, for example, body height, its unit like centimeters. Body weight in kilograms, for example. Counts of patients, they are just simply counts, but still, they are just counts represented by numbers. Dates, like for example, the 1st of December, for example, the 2nd of December, and so on. Also, these are numbers, like you can write them in numbers. Degrees of Celsius, degrees of Kelvin, and so on and so on. So all of these variables considered as statistical variables are typically represented in numbers. and it's versus we mentioned that this is meaningful to sum up them or subtract them two values of such a variable. Sometimes it's also called a numerical data type. It means that numerical means that it's typically represented by numbers. A qualitative variable, on the other hand, is typically represented by a few textual categories, textual values, like as we, for example, try to talk about it before, like a sex, males versus female. Yeah. Two categories, in this meaning, there are only two categories, like either male or female. Pain severity, for example. There's no pain, there's low pain, mid pain, or significant pain. It could be also a bit different. There's some of the clinical evaluation, how the pain could be significant for a patient. Tumor grading, like it's an Arabian numbers from 1 to 4. Tumor staging, it's like in a Roman numbers 1 to 4, and so on and so on. So it could be sometimes, as you can see here in tumor grading, it could be sometimes also described by numbers. Yeah. But don't be mistaken by this. We know that if there is like a tumor grading equal to 1, you know it from pathology. Number 1 of tumor grading is something which is related to carcinoma in situ. Yeah. It means that the carcinoma is still in one place, relatively limited, and it, for example, at the phase of grading 1, it usually doesn't have any kind of, let's say, signs of some infiltration to, let's say, deeper parts of, for example, of epithelial, or deeper parts of, let's say, some mucosa and so on. So there are some special definitions. There are some pretty detailed definitions about what is a grading number 1, but sometimes, or usually in Congress, it's called carcinoma in situ. On the other hand, number 4 could be described like, okay, it's like a kind of carcinoma, kind of cancer tumor, which is usually generalized. So they are kind of like a distant metastasis. Yeah, it means that it's generalized pretty in a, not, it's not localized only in some local part or in some local tissue, but they are not only affected the lymph nodes, but also some distant metastasis, and some distant organs or distant tissues are infiltrated by the tissue, by the tumor, yeah, by the cancer. So you can see that the numbers in tumor grading, they are used only for brevity, for this is kind of abbreviation, let's say. But all of the number 1, 2, 3, and 4, especially for 1 and 4, which could be good in this way, goodly defined, well defined as a carcinoma situ or generalized tumor. There is something like a definition, textual definition. What does it mean? So it's absolutely not meaningful, absolutely not feasible to take number 4, number 1 here in in the context of tumor grading and do the subtraction. Absolutely not meaningful. In spite of the fact that, okay, those are just numbers, yeah, but it's not simply meaningful to take some, for example, summation or subtraction of this, because the numbers are here only like they are only like they was only chosen for this purposes for as purpose for brevity, yeah, or something like this. But definitely there are some textual definitions behind them, and so it's not meaningful to subtract them. So in such a case that if there are still some numbers, they are only like a placeholders in some lists, or placeholders for some definitions and so on. So still not meaningful to subtract them or sum them up or something like this. So that's it. Sometimes the qualitative statistical variable is also called like a categorical data type, because typically male or females are categories. No pain, low pain, mid pain, or significant pain are also categories. 1, 2, 3, or 4, they are also in fact categories, and so on. Yeah. Okay, it's just a quick exercise, that quick problem set, that we are just going for the each of the following examples. We are going to decide whether it's a quantitative, so numerical data type, or qualitative, so categorical data type. Yeah. So total the score in percent points of students of one study group. So suppose that we have a sample of students, all of them underwent a test, and we got their results, and they are in percent points. So definitely those are numbers. Yeah. So some of them, for example, got 80%, some of them 50%, some of them 100%. These are numbers, and it's possible to make, for example, subtraction. For example, if you got two students, one of them got 100% in the test, another one got 80%. If you are about to do the calculation like subtraction, for example, 100 minus 80 is 20%. It's just a difference between is just 20% points. It's meaningful because it means that simply one of them is just better by 20% points or something like this. So definitely quantitative. The first case is just quantitative variable data type. A set of all July's days for a given year. So the 1st of July, the 2nd of July, the last of July, and so on. These are also numbers, and it's still meaningful to make, for example, differences between them. So still meaningful to calculate subtractions, like for example, the second one, or for example, the 10th of July minus the 1st of July means that there's a difference of 9 days. It means that, for example, the 10th of July is after 9 days after the 1st of July or something. It's still meaningful to do this basic arithmetics about it. So still, we can say that set of all July's days is also a quantitative data type. Set of all trams going through EP Pavlova station. I pretty believe you are pretty familiar with this station. Yeah. There are like trams number 6, number 10, number 25, and even more. I don't know them all. I don't know all of them, but those trams are labeled by numbers. Yeah. But we know that it's not so much meaningful to, for example, calculate their difference. Like if I'm about to calculate 10 minus 6, okay, like technically I can do it. Like 10 minus 6 is 4. Okay, I can do it. Technically I can do it, but it's not meaningful because the numbers for the terms are simple. Like they are just something like this is like they're indexing some list of yeah, all the terms in Prague, or some kind of schemes of, yeah, some kind of schemes of traffic in Prague or something like this. So it's only for some catalogization purposes or some listing purposes. Although it's relatively easy for people, like normal people, to get some, let's say, orientation in a like operating traffic in Prague. Yeah. So it's even easier due to the fact that they are labeled by typical numbers, because people are usually able to remember some, let's say, limited number of numbers, but it's still easier to remember some numbers that, for example, some longer words or something like this. Yeah. So that's from this reason. So despite the fact that they are labeled by as the numbers, using some Arabic numbers, still we know that it's a qualitative statistical variable type, yeah, because the numbers are not meaningful to do any kind of calculation with them. Names of all CVTR genes mutations. Maybe you know that CVTR gene is important for determination of cystic fibrosis, which is the most common or most frequent autosomal recessive kind of genetic disease. Definitely what are the symptoms and so on. The most significant mutation is, as far as I know, maybe something has changed from my times of my medical studies. But what I studied like before 8 years, studied F508 deletion is the most important mutation of CFTR gene, and there are maybe 200 of others, say, or something like this. So they are like labeled by some alphabetical character or some alphabetical string or something like that. So these are not numbers. These are some strings. So this is also qualitative variable data. If, for example, we have a sample of 20 patients with cystic fibrosis, and all of them got a different mutation, all of them will be labeled by something which will be similar to this. This is not possible to do any calculations using these labels, because these are simply categories. So definitely qualitative data type. A pain severity measure using visual analogous scales. These are numbers from 0 to 10. This is a relatively tricky diagnostic test for pain severity. Because it could look like, for example, that you simply provide a patient with a rule, for example, from 0 to 10 centimeters, and he or she is about to point out, for example, where he or she thinks that or feels that his or her pain is about. For example, it could be 3 centimeters from 10, or 5 centimeters, or 7 centimeters from, or 9 centimeters from 10, and so on. Or also we can try to inform him or her before, like for example, visual scale level of pain severity. Let's say about 10 is something which is, as far as I know, or number 9. Number 9 is sometimes called that number 9 is about childbirth, like like a gravid woman is just like a childbirth with no anesthetic and any kind of anesthetic drugs. Yeah, so like a nature childbirth. It's about 9, as far as I know. So the patient would be also informed about some, let's say, example cases in before. Yeah. But if the patient got this kind of rule, like to point out where he or she thinks that his or her pain level is on the rule from 1 to 10 centimeters, these are the numbers, and this could be tricky. It could be like numbers that it could be meaningful to take some difference. For example, that number 10 is by 5 larger than number 5, but also this could be understood as categories. So this is tricky. This is tricky. It depends on context. Hard to say that if whether this is a quantitative or qualitative example. That's why I just listed here, because it's tricky and it depends on a context. It could be both the qualitative or quantitative. It really depends on the way how the data was measured, how the data was collected, whether a patient was simply informed before that some number 9 stands for some typical situation, number 8 stands for some different typical situation, number 2, for example, stands for another typical situation, and he tried to or he tried to imagine himself in a situation. Okay, it may be the similar pain level or something like this, or the second in such a case it will be rather qualitative statistical type. But in the case that he got a rule from 0 to 10 centimeters, and he was about to he was just about to try to point out where exactly is his or her level of pain. For example, it was at 5.3 centimeters. In such a case, I would rather say it's like a quantitative data type. Number of all childbirths in one hospital per one night. These are just simple counts of all childbirths in one hospital per one night. So since there are counts, it could be, for example, say, okay, the next day there are, for example, 10 childbirths. The previous day there were 5 childbirths. 10 is by 5 large and higher than 5. Definitely some substitution is meaningful. So this is a quantitative data type. And the staging of colorectal carcinoma, 1, 2, 3, 4. We already talked about this. These are numbers, but still it's not meaningful to take any subtraction or to take any arithmetical calculation with them, because there are some textual definitions behind the numbers. So it's just about the definition behind it. So this is meaningful to take the subtraction. We absolutely not meaningful to, for example, tell that okay, 4 is by 2 larger than 2, 4 is by 1 larger than 3. It's not possible to think about it this way. Yeah? So this is definitely qualitative statistical variable type. Well, and now we are moving to the part that I'm going to introduce some basic, let's say, characteristics, some basic statistics about the qualitative variable description. Some of them are, I would say, relatively easy. The concept behind them is relatively easy, and I would also say that you could be pretty familiar with them. So it's not necessary to talk about them, for example, for two. We are just going to talk about them very shortly. So yeah, something like this. So as a repetition, for example, qualitative variable description could be, or for qualitative variable could be, for example, body height or glycemia or weight and so on. We can use either numbers, some numerical characteristics, or some graphical approaches. So using the numbers, they are typically in Western, in English textbooks of statistics, there are these three words. They could be a bit different, but typically they write down center, spread, and shape. The center stands for typical measures like means or medians or modes, like mean, median, modes. Yeah. Also good to know about all of them. Arithmetic mean, median, and modes. This is the characteristic which belongs to the center. Spread is sometimes also called a variability. Yeah. Spread or variability. It means that center is like described by some kind of characteristics which can tell us where is like the typical value, where is the typical value of our qualitative variable in our sample. So it's typically close to a central, like a central let's say central density of our data, or some central tendency of our data. So where is the most of the data, or where the data typically are, for example, located around which value, around which number. So these are the numbers which typically data should be located around, like arithmetic mean, median, mode. Spread is about the variable. So it means that, for example, how close or how far are the values located around the central statistics or central metric. So range is typically and relatively simple measure of spread. It's just a difference between maximum and minimum. So what is the difference in between the maximal and the minimal value in my sample? Standard deviation and variance. Those concepts are, let's say, more advanced, but not so much. So I'm going to talk about them in a brief. And the last property of our sample data is the shape. But there are two metrics like skewness and goodness, but I'm not going to talk about them. Typically, it could be, for example, it could be rather, let's say, extracted this piece of information like a shape is rather to be, let's say, extracted from, let's say, some plots or some graphical visualizations rather than from the numbers. It could be kind of misleading. And using the graphical approaches, using some plotting, typically there's a box plot and an histogram. These two plots are good to know about them, and I'm going to talk about what, maybe not how to build them, how to construct them, but rather how to interpret them, how to understand them. So arithmetic mean, absolutely something which you are familiar with. So there's no need to talk about it for a longer while. If you have numbers like x1, x2 till xn, their arithmetic means simply follows this form. I'm just going to sum them up and divide them by their count here. So it's as easy as this. Just sum them up, divide them by this count. It could be also written in this, let's say, shorter way, but this is definitely, I think it's pretty easy how to do it. So assuming that we have those 5 people with those body heights here, and we are about to calculate their arithmetic mean. We are about to sum the heights as we can read them here and divide by 5 because there are 5 people here. So what we are going to get is just a arithmetic about 171.6 centimeters. How many different arithmetic means could have one sample of given values? Only one. If the values are like here, if they are simply given, so those 5 values are still the same, there is no way how to get let's say, different number than this one, since we are about to do the summation and then the division by their number, so by their count. So only one. So if the values are simply given, then the value of arithmetic mean is absolutely what's like predefined. What is geometric distribution of the arithmetic mean? This may be a little interesting and know about it if you want to. Estimate we have n weights, 1 gram. So all the weights are of the same weight, and you are about to hang them up on a long rule of negligible weight. It means that the ith weight is exactly on a point of xi centimeters. Then an arithmetic mean of x bar of the values x1, x2 to xn is equal to the system center of mass. You know what is center of mass from biophysics? This is the first example. We have, for example, numbers 2 and number 4. Arithmetic mean of number 2 and 4 is just a summation and division by 2. So 6 number 2 is 3. And you can see that, okay, if I have 2 and 4, definitely for example, just to use, for example, to get this system in a some kind of the steady state, like to, for example, hold it in its center of mass. It's in a number of 3, because if I'm going to hold it here, just keep it here, definitely it's going to be in a steady state, because I just keeping, if I'm keeping it here, I'm keeping it in its center of mass. Similarly here, 2, 4, and 6, its average is 4. 4 is in the middle of it, so it's going to be in steady state. So definitely, if I'm going to keep it here, I'm keeping it in the center of mass, and so on. So it could be, if we derive it, it's that arithmetic mean it's all the time in the center of mass, where the weights, the system which are created from the weights are, let's simply hanged up on a let's say location of points which are related to the numbers for which I'm about to calculate the arithmetic mean x1 to xn. Median. What is a median? Median is the value of a middle observation. It means that if we, assuming that we have observation, we are sorted from the lowest to highest, or it also works for if we are sorted from the highest to lowest. But if we are sorted from the lowest to highest, a median is just a value in the middle, so it's a middle observation. So it means that roughly half of observation is lower than the median, and on the other hand, the other half of the observation is higher than the median. I just wrote down this roughly. It could be exactly, yeah, but from some reason, for example, if there is just simply a even number of let's say values in my sample, then there is no middle value. Yeah, there's no, because there's just even a 2 or 4 or 6 or 8 numbers. It means that there is no like the middle number. So that's why I just wrote that roughly. So how to calculate the median? If there are n numbers like x1, x2 to xn, you can find their median as, as follows. So we choose first sort the numbers from lowest to highest, and then if the n is odd, it means that we have like 1 or 3 or 5 or 7 or 9 and so on numbers. Then x tilde, which is usually how the median is labeled by or marked by, x tilde as the middle value. So for example, if we have 3 numbers, and sorted 3 numbers, the number in the middle is the second one. If we have 5 numbers, the number in the middle is the third one. If we have, for example, 9 values, by 9 numbers, the value in the middle is just the 5th one, and so on and so on. And in case that we have the n is even, so we have, for example, 2 or 4 or 6 or 8 or 10 numbers, then we are about to calculate the arithmetic mean of the 2 middle values. So for example, if you have 10 values which are sorted from the lowest to the highest one, so the values which are in the middle are the 5th one and the 6th one. So I'm about to pick the 5th lowest value and the 6th lowest value, and to calculate the arithmetic mean of them. Yeah, this is the way how to calculate the median. So what is the median of the following 5 body heights? The people here are already sorted from the lowest to highest value of the body height. So the median is, you can see that the median is like the value in the middle, and since there are 5 people, the middle value is the third one here. Yeah, so median is labeled by x tilde. X tilde is just 171 centimeters. So there's only, in such a case that we have one given sample, there could be only one given by one predefined median. Geometric interpretation of median, it's like if we have the values x1 to xn and try to highlight them on a longer rule, so the ith value is highlighted exactly at a point of xy centimeters. The median is of the values is a number with minimal possible sum of distances from the values, from all the values. So it could be, for example, nicely visible here, for example, 2, 4, and 6. The median is in the middle, so it's 4. And you can see that if the median will be something else than 4, then the distance from 2 and 6, distance from 2 and 6 is in summation constant, because if I'm going to switch to shift the median a bit to the right or to the left, the distance to number 2 will be a bit like, let's say a bit lower, but the distance to the 6 will be by the same amount, by the same number of centimeters will be a bit higher. So the summation of distance from 2 and 6 to number 4 is still the same. So to minimize the summation from number 2, or distances from number 2, number 4, and number 6, means that since the distance from number 2 and 6 will be still the same, and in the variant it will be just 4, because 6 number 2 is 4. I have to minimize the distance of median from number 4. It means that to minimize the distance means to keep the median equal to number 4, because the distance is in such a case consequently equal to 0. Yeah, so that's how to minimize the this summation of all the distances, and that's why if there is odd number of count of all the numbers in my sample, the median is exactly the middle value, and they are sorted this way. So there's just a geometric intuition how to interpret this. What is a mode? Mode is the most frequent value in this example. So if we have sample of 10, 11, 11, and 12, the mode is 11, because 11 here is in this very small sample. This is 2. There's a 2 times. 11 is 2 times here. So mode is 11, but don't be afraid. Don't be missing by this. Don't be confused by the fact that if the number 11 is 2 times in my sample, it means that mode is 11, not to its frequency. Frequency of 11 is 2, while the frequency of number 10 and number 12 in my sample is equal to 1. Okay, it could be, but if the frequency of 11 is 2, that's why 11 is mode, because it's the most frequent value in my sample. But mode is equal to its value, not to its frequency, but to its value. So 11 is mode. This is example. So find the mode of its following 5 body heights. This is a tricky part. This is a tricky task. You can see that number 152 centimeters is only 1 time in my sample, but both the numbers 165 centimeters and 176 centimeters, they are 2 times in my sample. It means that both the 165 and 176 centimeters are are modes. Sorry, both of them are modes. That's why I always did this kind of question here, because it could happen that there are two or more, or one or more, but it could be 2 or more modes in my sample. So in this case, you can see that there are 2 modes. So it can be at least 1, but it could be even more modes in my sample. So that's exactly the situation, that there are 2 modes, 2 different modes in my sample, because both the values 176 and 165 are the most frequent values in my sample. So, but their frequencies are even equal, because their frequencies are 2. Yeah, their absolute frequencies are 2. So both of them are modes of my sample. Arithmetic mean and median. We should find arithmetic mean and median for the following 2 samples. It's relatively simple. Just to calculate arithmetic mean and median. Median is in the middle, so median for the first sample is 3, and arithmetic mean you have got to sum them up. It's like 1 plus 2 plus 3 plus 4 plus 5, but divided by 5, it's equal also to 3, because it's just a 15 divided by 5, it's 3. So we can see that both the arithmetic mean and median for the first sample is equal to 3. For the second sample, there's something a bit strange, because you can see that the first 4 values are exactly the same as for the first sample, but the last value is equal to 90, and it's pretty well, it's like absolutely different number than the rest of the remaining numbers here, because they are pretty close to 0. They are like small integers. 90 is, let's say, more than 10 times larger than all of these numbers. So it's kind of, let's say, I would say it's kind of outlier maybe in between these sample. But still, what is arithmetic mean? It's like 1 plus 2 plus 3 plus 4 is 10 plus 90 is 100 divided by 5 is 20. So arithmetic mean is equal to 20, while the median is equal to 3, still to 3, because as you can see, while the arithmetic mean is sensitive to all of the numbers, so to the lowest one to the largest one, and here we can see that the lowest one is relatively close to the remaining of them, but 90 is pretty far from the rest of the numbers. So that's why the arithmetic mean for the second sample is much more larger than you expect. For example, it's much more larger than the remaining numbers because of this high value here. Yeah. So that's why arithmetic mean is not so much what's like not so much suitable for samples which are not so much symmetrical, which for example can which are asymmetric ones, and also they can for example include some values like kind of suspicious outliers or something like this. While the median is absolutely insensitive to the higher to too high or too low values. You can see that it absolutely doesn't matter if there is 90 or 100 or 1000 or 1 million. It absolutely doesn't matter. And you can see that number 3 is still median, like it was in the first sample. Yeah. And it means that median is much more suitable to be used for the second sample than the arithmetic mean. Arithmetic mean is very sensitive to the outliers, and 90 could be considered to be outlier in the context of the remaining or the first 4 values, like these values. And you can see that unfortunately, arithmetic mean is too much sensitive to outliers. On the other hand, median is absolutely insensitive. So median is very robust to be towards the outliers. So that's why it's my question. You need to measure the like work better for asymmetric data. This is asymmetric data. These are pretty symmetric. Yeah, these are like +1, +1, +1, +1. So if this is like a pretty symmetrical one, sample both the arithmetic mean and median works good. Yeah, but if there is kind of some asymmetry, and this is definitely kind of asymmetry, is kind of maybe let's say outlier, but we cannot prove it like mathematically. But it seems that 90 is much more larger than the remaining numbers, so 90 seems to be outlier. So there is outlier which is a source of asymmetry here. Then you can see that median is much more better metric to be calculated about the sample than the arithmetic mean. Arithmetic mean could be shifted to the higher values towards the outlier values, and it means that it's typically bias the estimation of central tendency of the sample. The central tendency of this sample is somewhere close to 3 or maybe 4, something like this, which the median works in this way. But 90 is something which simply shifted the arithmetic mean, the average towards the higher values. So it's kind of it's like a distorted this way. So what is the take-home message? If you have asymmetric data or data that contains, for example, one or more outliers, use rather a median than an arithmetic mean. This is like an example where you can see that median is much more better to describe this sample than arithmetic mean, which is like shifted towards the higher values because of this very large outlier. Okay, now we are just moving towards the variability metrics, towards the spread metrics. So a range is pretty easy to be calculated. It's just a maximum value minus the minimum values. So it's just a distance from the maximum value to the minimum value. So if we have this our still the same sample with our 5 people, range if we are about to calculate the range for the following 5 body heights, you can see we know that it's simply just about picking the highest one and the tallest one and the shortest one and just calculate the difference between them. So just 194 minus 152 centimeters, it's 42 centimeters. So this is the range, yeah, min max or range. It's sometimes labeled by min max, sometimes like it's called range, depends, but simply the range of the values, like different between the height, the maximum value and the minimum value in the sample. Standard deviation, maybe you remember this from biophysics. There are some tricky parts about the standard deviation, so I'm not going to talk about them because it's more into statistics, and by this we would just get pretty far from medicine. So if we have values like x1, x2, and xn, the standard deviation follows this form. It's like summation of the deviations differences between the observations and it's their arithmetic mean. So firstly, it's about to calculate arithmetic mean. This is which should be that should be pretty simple. Then we are about to calculate the differences xy minus xi minus x bar, like it's the arithmetic mean. Put the square values of them and sum them up for all the n observations, and then we have to divide it by n minus 1. Sometimes some students ask me typically why there is n minus 1 and not n, like why this is not an arithmetic average from the square values of these deviances. This is called Bessel correction, and the like the answer to this phenomena why there is n minus 1, it could be answered by some, let's say, more advanced statistics. As I told you, it's called Bessel correction, and by using n minus 1, we got like a unbiased estimate of standard deviation. Yeah. So there are some more technical and mathematical reasons why there is n minus 1 instead of n in this denominator. And maybe an easy explanation could be that if I'm about to calculate the variability, it's better to variability could be also an estimate of, for example, some measurement error. Yeah? And if we are about to calculate measurement error, it's far more better to overestimate our measurement error, because it's better to overestimate the error than underestimate it. Definitely, I think that you intuitively understand this is better to overestimate the error than the underestimate it, because yeah, overestimate means that in the very end we could be, for example, surprised, relatively like happily surprised that, for example, the error wasn't so high. So it's better in the beginning of our analysis to overestimate the error. So that's why we would like to divide this summation by a bit lower number, and n minus 1 is definitely lower number than n. And this is like not an explanation in mathematical notation, in mathematical way of thinking, but it's maybe kind of intuitive, yeah, why there is n minus 1. And Professor Bessel proved that it's also important to calculate n minus 1 term in the denominator, because of the fact that then the estimate for standard deviation is unbiased. Yeah. The variance is if I'm just going to calculate this, but not taking the square root of it. So it's just the all the terms below the just until the square rooting. Yeah. So just this is just a variance. The unit of variance is the squared original unit. So if x is in centimeters, then a unit of variance is in centimeters squared. If x is in centimeters, then a unit of standard deviation, on the other hand, is also in centimeters, because of this square root. Because of the square root is going to be also in the original units. That's why standard deviation is more handy than variance. Yeah. Intermezzo, I'm not supposing we are able to calculate it from yeah, with no some software, or with some calculator or whatever. So standard deviation for these 5 numbers is like this value. Yeah. So firstly I have to calculate arithmetic mean, then these deviances, their squares, yeah, just powers 2, sum them up, divide by n minus 1. I'm going to get 15.4 centimeters. If I were to power this to 2, just take a square, it should be more than 225. And 15 power to 2 is 225. So it's about above this, and so 237 centimeters squared. It's a variance. So this is a standard deviation, and this is a variance. Yeah. Okay, now we are starting with the graphical approaches. So I'm going to maybe, yeah, I think I'm able to finish the lecture maybe in 15 minutes. Like we started a bit later, yeah. So I hope that I'm able to do it. Okay. So what is a box plot? Box plot is this kind of plot. It's original. It was proposed by Professor Fisher, who is both a physician and a medical doctor from Great Britain. Somewhere that was about like 1890 and 1910, something like this, in these years. And what is this box plot? What is it plot about? So the thicker line, the middle line here, stands for median. So I can see that if I just go to plot of let's say what I cannot say is how many people, how many individuals was in my sample, but I can see that I simply measured their body height, yeah, in centimeters. But I cannot say there are 10 or 50 or 100 of people. I absolutely cannot say it from seeing only from only using a box plot. It's not possible to say this, but still we can say relatively let's say we can get a relatively uh, good idea what is our sample and our statistical variable about, because this box plot is still the same logic regardless of, for example, some kind of, let's say, aesthetical, yeah, some kind of aesthetical plotting and so on. So there could be some aesthetical features there, but still some of the main properties of box plots are still the same for the last 100 of years or something like that. So the thicker line here stands for median. So the median value of my sample was about 175 centimeters. It stands for median. There are also this green box, let's say, as its lower and upper bound. The lower bound here is equal to maybe 170, and it's equal to the first quartile. The first quartile is a value, a number, which splits my sample to the lowest 25% and the highest 75%. So it means that in my sample, there are 25% of people, 25% of individuals whose body height was lower than 170. On the other hand, this is the third quartile, and it splits my sample into the lowest 75% and to the highest 25%. It means that it's, in my case, 181 centimeters. It means that in my sample, there were 25% of people whose body height was higher than 182 centimeters. Yeah. So this is like so one more time. This is median. This is the first quartile. So 25% of people simply lower than their body height was not like lower than 170 centimeters, and this is the third quartile. It means that there was about 25% in my sample, and their body height was simply higher than 182 centimeters. And there are some, let's say, error segments. Like it means that in this case, in the upper case here, this is the maximum. It means that there was a guy, an individual in my sample, so that his or her body height was almost 200 of centimeters. Yeah. And in this case, this is not a minimum, because this could be a minimum if there will be no this separate point here. So this is like a tricky part. If there is this kind of plots, separately plotted points, it means that the minimum body height in my sample was just 141, let's say, or 42, something like this. And if it is plotted this way, so it's not covered by this error segment, it means that it was so low that it was like it could be a suspicious outlier. That's why if this is like lower than, if I'm going to calculate the difference between the third and the first quartile here, so in other words, the height of this box, and multiply it by 1.5, I'm going to get this distance from the lower quartile, so from the first quartile to this segment. And each values of body heights which are below this bound, let's say below this margin, they are considered as suspicious outliers because they are too low. The values of these body heights are too low. They are according to our prior expectations, they are simply too low. So yeah, so it means that we have to, for example, check these values, check the value for which is pretty low. It's like too low. It's not so much similar to the rest of the data. So this is the way how the box plot can tell us that, okay, there's one value which is a bit messy, and we have to, for example, check it if there is no problem, some kind of problem with this value, for example, to redo the measurement if we are able to do it, to redo it, and so on. So this is the way how in a box plot usually we can illustrate or demonstrate or indicate that there could be a outlier. It looks like this. So it means that this is not a minimum. This is like a kind of artificial minimum. Yeah? It would be like a normal. It could be just a value of the minimum value if there will be no outlier. Yeah? But still, if there is an outlier or a suspicious outlier, then this is not a minimum. This is like a, the lowest possible body height, which is still still supposed to be like a normal value, a normal non-outlier value of a body height, something like this. But if there is even lower value, and it is a suspicious outlier. And that's how boxplot works. Okay, there's just a quick intermezzo, and there are 3 boxplots, and we are about to decide which one of them doesn't make sense. So there's a number of childbirths per night in a given hospital, for example. So it means that median value is about 20, 22 maybe, 21 maybe, and all the values are positive. There are no outliers. I think that this is possible. It would, for example, be a rather large hospital. This is possible to have, for example, even 30 chambers there. So this, for example, the sample of the data for creating of this box plot will be, for example, let's say 30 values of, for the last 30 nights in a given hospital, such that in per each night there were some evidence how many chambers was evinced by the given night, and so on. So it was repeated for all the night, for each night, for the last month, something like this. So from my point of view, this could be possible. There is no like something strange about this box plot. The first one, there's a glycemia in millimoles per liter. Also, there are positive values. Median is somewhere between 4 to 5, which is pretty normal. This is also important. I forgot to tell this here. But if we know that there is like the third quartile, and this is the first quartile, and both of them are about to split, they simply split the lowest and the largest 25%. It means that the rest of the values is like 100% minus 25 minus 25. It means this box could cover middle 50% of all the values. So it means that the 50 values of my sample is in between, let's say 4 to 5.2 or something like this in millimoles per liter. So it's a relatively handy piece of information that 50% of my sample is in between these two values, like roughly 4 to 5.2 or something like this. So all the values are positive. There's some outliers, kind of hypoglycemia below 2, but still possible. So this could be possible. Let's say in the very beginning, I just got a sample of patient, and I just had to measure their glycemia. So there could be, for example, 100 patient, and I got 100 glycemia values, and created this box plot. This is possible. There is a number of hours of anatomy studying per day, probably the freshman year of medical studies. So it means that we are about to check if this is possible. So there are some lower values. Okay, 10, like the median value is 10, is still relatively high to study 10 hours per day. Our anatomy or something is okay. 24, okay, it's pretty rare, but still possible. But what is not possible is that it's not possible to study, for example, 32 hours per day, or even 48 hours per day. Is absolutely not meaningful. So there are some two values which are not, let's say, feasible, and that's why the last box plot here is absolutely, it simply doesn't make a sense. Yeah, because there are some values for a number of studies of anatomy per day, and which means that there is the number of hours per day is of course limited. So it's possible to study 32 or 48 numbers per day. That's it. Okay, I'm going to maybe you know what, I'm just going to let's say finish the digital statistics, and maybe we can move the inverse statistics to the, let's say, we'll see, but we can move it, for example, to the beginning of the next next lecture. If I inform you in an email that we are going to continue the next Monday. So we will see. But I think I will just finish this list for now, and we'll see. Just not to exhaust you too much. So an histogram. This is about a similar problem. So we have body height in centimeters. We can say that we have the same sample like here. Also, for the first, let's say, for the first impression, it's hard to say how many individuals was in my or is in my sample. But I will try to like to explain you how to get the total number of individuals in my sample from this plot. So in this on the horizontal axis, the original variable is plotted. Yeah, you can see that there are just the like a tenths of centimeters plotted here. So this is also the result of body height. And on the vertical axis, absolute frequencies are plotted. It means that, for example, looking at this bar here, we can say that okay, there were like 4 people in my sample, so that their body heights were in between 150 to 160 centimeters. Yeah. For example, this bar, it means that, okay, there were, let's say, 20 people, or maybe 21, 20 or 21 people, so that their body heights in my sample, so 21 people in my sample, so that their body heights were between 160 to 170 centimeters, and so on. For example, this is the tallest bar. There were about 40 people in my sample, so that their body heights were in 170 to 180, and so on and so on. So it means that by using histogram, I can get a relatively nice idea what is the distribution of my data. So I can see the maximum individuals in my sample got their body heights between 170 to 180, because this is just the tallest bar here. On the other hand, for example, the minimum category, the category that only 1 or 2 guys are there with body heights in between 140 to 150 centimeters. So yeah, this was really rare. So, for example, I can say that the modal category, or just the modal category, yeah, modal category of my body height is this one. So in between the 170 to 180 centimeters. Because it was just the most frequent in my data. It's a model category. And also we can see that it was like a kind of one peak, and it was like a typical for my sample was typical that the majority of all individuals in my sample got their body heights between 170 to 180 centimeters, and towards the higher or to lower values of body heights, the numbers of individuals just decrease. Yeah, you can see that it's relatively rare to get too low body height, and also on the other hand, it's relatively low to just relatively unlikely to have guys or many guys with lots of relatively large body height. Yeah. So this is the storytelling behind this plot. So it tell me that the center tendency is somewhere around 170 to 180 centimeters, and the relatively low and relatively high values of body heights are rare in my sample. Also, we can try to, for example, follow the tips of my bars, and with some level of imagination, you can try to imagine there's just a kind of bell-shaped curve around the tips of my bars, and some of the well-known bell-shaped curve is curve which is called Gaussian curve. So I just wanted to talk about it. There's good visible here, for example. Yeah, so this is about histogram. So as I told you before, this is possible to realize how many guys was in my sample, because if I'm just going to calculate or sum up the heights of my bars, so sum up the individual frequencies of individual groups, individual intervals of body heights, I can give the total number of individuals in my sample. So it's like 2 plus 5 or 4 plus 20 plus 40 plus maybe 28 plus maybe 7. So if I just sum up those 6 numbers, I will just realize how many individuals is in my sample. This is how to get it. It's not possible to do any similar kind of calculation using the box plot. It's not possible. but it's possible to realize how many guys was in my sample using the histogram. That's maybe why a histogram could be, from this context, supposed to be more informative. Yeah, but it depends. It really depends. On the other hand, for example, we cannot say what is the median here. Yeah, so median is pretty nicely plotted by box plot, but it's not plotted using histogram. Okay, what is also important, I'm talking about this, is the number of intervals in the histogram could change the story behind the data. Okay, I just try to let's see. I just try to plot the same sample in two ways. On the left hand side and right hand side pictures and images. Both of the samples which are behind these two plots, the plots look absolutely different, but the samples used for creating the left hand side and right hand side plots, they are absolutely the same. There's only one sample plotted in these two different ways. And you can see that if I try to do it the first way here, I got like I would got the first idea. Okay, there is only one peak, there is one maximum somewhere around 170 and 180 centimeters. And okay, the vast majority of all the individuals in my samples are maybe in between 160 to 180 centimeters. Okay, pretty normal, why not? But typically, by using only six bars, six intervals, uh, I can suppose that there is only one mode or one peak in my data. There is only one maximum of frequency or something like that. And using the absolutely the same sample here on the right hand side plot histogram, you can see that it looks a bit different. Number of histogram, but number of intervals here is much more larger. It's about maybe 20 or 25 or maybe even 30. It's simply larger. There's only 6 intervals here. There are maybe 30 intervals here. So we can see it looks like there are two peaks. Like one peak is here and one peak is here. Like, okay, it's like you can see it's statistics. Yeah, I'm sorry. It's like statistics. So it's not like it's not like too much determined that there will be like one pretty maximum and another one maximum here. Okay, it's like there's kind of oscillation, but still using some feeling, you can see that we can try to imagine that there's one maximum here, one peak here, and the second one peak here. Yeah, so it looks like using the same data but different histogram using the different value of intervals, the number of intervals. The data can tell me, like in quotation, the data can tell me that there are in fact two populations mixed up in one sample. And in fact it is, because the data are simulated here, but I simulated data the way that the population in this sample, still the same sample, but plotted in these two different ways. This is just a mix of females and males, because we can see that for the male part of the population, there was like the median or maybe mean value somewhere here, like 175 centimeters of body height. It's, I think, feasible. And for the female part, maybe there was like 50-50 percent of both the parts. So the female median value or mean value is somewhere here, like it's maybe 160 something, because it's another peak, and in the middle of this peak there's like 161, maybe 162. So it means like the take-home message, and I think this is important. The take-home message is that the plotting of histogram could be done like better or not so much, not so better, not so good. So this way it's relatively good, because the histogram told us that there could be two different subpopulations in my sample, and in fact it is, because there's like a subpopulation of males, and the second subpopulation those are just females, and it's relatively visible from this histogram, but it's absolutely not visible for the first version of histogram. It's not possible to be like detected anyhow from the first one, because it looks like there's only one peak. Absolutely no way how to realize that there should be two peaks. So it means that the number of intervals in histogram could be, for example, could be chosen a good way or in a bad way. And it means that it really depends on this parameter, how to build up an histogram. And the law, or just a rule how to do it, rule of thumb, is called Sturges law. And it tells us that the number of intervals, which is like marked here as k, is equal to this formula. So if we know that n stands for a number of observations in my sample, we should do logarithm of n with a base of 2. So for example, I just didn't list the example here, but it means that, for example, if n is 32, then a logarithm of 32 with base 2 is equal to 5. It means, in other words, what is the exponent of 2 to get 32? So I have to power 2 to 5 to get 32. And that's the logic of calculation. Simply just logarithm with a base 2 from the given sample size. And you have to round it to the closest higher integer, for example. But important part is just so the strange brackets here tells us that we should round it to the closest higher integer, but it's not important. Important is that we have to calculate logarithm of n from with base 2. So if there is, for example, I think that the number of guys in this or induced in my sample was like maybe 1,000 or maybe 3,000, something like this. Yeah. So it means you can see it was like 300 multiplied by, let's say, yeah, I don't know, maybe 3 or 4, something like this. So it was n was simply larger than 1,000. And a logarithm of 1,000 with base 2, maybe you know that 2 power to 10 is 1,024. It's like a well-known number. So the number of intervals should be at least 10. It could be rounded up, yeah, but at least 10. So 6 intervals is pretty low. Yeah. So it has to be a larger count of intervals. And as we can see, really only 6 intervals was too low number, that the storytelling behind the data and using this histogram, well, it was simply, it's still hidden. Yeah? We cannot detect that there are 2 subpopulations. But using, for example, 20 or 30 intervals, it's nicely visible here that there are 2 subpopulations. So that's the take-home message, that if since it could be done better or not so much bad, not so much good, it's a good idea to follow some rule of thumb, and the rule of thumb for the number of intervals is this. So in case that you are about to, for example, create some histogram, it's possible to do it in Microsoft Excel, for example. Try to follow this formula, because I think that Microsoft Excel is not a statistical software, and the way how to plot histogram in Microsoft Excel is that you have to manually determine how many intervals we are about to create. So in such a case, use the Sturges law, which means that you can unreveal, for example, some let's say hidden knowledge in the data. But by using only a few numbers of intervals, it could be not so much informative. Well, so last few minutes, let's say. Also, to change the normality. Normality is a relatively nice property of data. It means that if the histogram looks like this one, you can see that the tips of the bars simply follow. This is not like, it's not like a plotted here, but if you try to imagine that there is like a curve above the tips of the bars, it should simply follow the well-known bell-shaped curve, and it's called like normal curve or Gaussian curve, and it could look like this, like the well-known Gaussian curve. So it could be checked typically visually using the histogram if there is like a possible assumption of normal distribution of data. It's usually typical for some let's say other application of statistics, like some inferential tests and so on. But yeah, for this moment, it's just about the usage of a histogram. It could be used to check whether there is like a assumption of let's say assumption of normality distribution or not. If we can assume that a variable follows a normal distribution, which can be checked using a histogram, we can also use this kind of let's say, results which are pretty, let's say, they could be both important, both interesting, but it could be relatively important for us for some, let's say, for some ways of thinking about what is, for example, the variability of the problem and so on. Because we can follow these rules, like this was derived using some integration, but forget on this. So if we know that the data follows normal distribution, so their histogram looks, for example, like this. We know that 68% of all values is covered by this interval, like average minus standard deviation, average plus standard deviation. These are the two numbers there. Average minus standard deviation, average plus standard deviation is just one interval. So two values, two bounds, lower bound and upper bound. And in this interval, there is 68% of all values covered by this interval. Similarly, if I'm about to subtract or add two standard deviations, not only one, like in the previous case, but two standard deviations, I can say that there is 95% of all values covered by such an interval. And finally, if I'm about to subtract three standard deviations and sum them up, three standard deviations, I can get another interval. And there are 99.7% of all values in this kind of interval. It's also plotted here, but the most handy information is maybe the second one, that 95% is relatively large percentage, so it's almost 100%, but still the interval is not so wide. Yeah? It's still relatively narrow. So this is maybe the most important piece of these three rules. Also, like if I accidentally ask you how let's say wide should be the interval which cover 100% of all values, then the answer will be pretty simple. You have to subtract and sum up like the infinity value of all the standard, because it was like from minus infinity to plus infinity. Yeah, because it's like a if you like to have 100% of, if you like to be 100% sure that our interval would cover all possible values, there is no way to subtract, for example, three, or subtract or sum up three standard deviations. We have to subtract and sum up like the infinity number of some standard deviations. So it relies from minus infinity to plus infinity. So this is not so much practical. What is practical is the second rule. 95% of all values is covered by this interval. This interval is still relatively rather narrow, but it's possible to cover relatively high value of percentage of all possible values, considering that there is like an assumption that variable should follow the normal distribution. Okay, if there is no assumption that a variable should follow or could follow the normal distribution, then the rule is a bit different. This is maybe relatively tricky, because if I cannot assume that the variable can follow the normal distribution, then it sometimes, regardless of the fact I can assume it or I cannot assume it, in both the cases, so in all cases, in this interval, there is at least 75%, because you know that at least 75% could mean also 95%. So this rule, or this this theorem is stronger than this theorem. Yeah? But this theorem holds always. This is always true for all data, whatever kind of data all around the world. But this holds only for data where we have to assume that a variable follows the normal distribution. So that's why this theorem is stronger. But there is no assumption for this theorem. And in this interval, like average minus 2 standard deviations, average plus 2 standard deviations, there's like 75% of all values covered by this interval, and 75% is also relatively high percentage. Not so high like 95, yeah, of course, but 75 is also good. And in interval minus 3 plus 3 standard deviations, there's like almost 90% of all values covered by the interval. So also without any assumptions. It's come from a very well-known Chebyshev's inequality. Yeah. You already heard the name of Chebyshev. Chebyshev, it was like a Russian mathematician or statistician, and yeah, Markov and Chebyshev, they derived many inequalities and many theorems, central limit theorems also in statistics. So for example, there is in this plot there is just an example of how it could look like if there is no assumption of normal distribution. Here you can see it. For example, here absolutely we can feel free to assume that there is a normal distribution assumption. Of course, I have a very nice histogram where it's very relatively easy to assume that there is like a Gaussian curve above the tips of the bars there. But here, on the other hand, it's hard to imagine something like bell-shaped curve here, because this is like rather similar to some kind of rectangle or something like this there, with some level of variability or some level of stochasticity. But it looks like rather a rectangle. But this looks very nice like a Gaussian curve. Okay, so four last slides, I will just do it very quickly, and I will just move the statistics to the beginning of the next lecture. Just for a quality description, this is pretty easy. So as a quick repetition, it could be blood type AB, 0, tumor grading 1 to 4, sex, male or female, and so on and so on. So we can use both the numbers or graphical approaches. Still the same like it was in quantity variable description, but here. Using numbers, we use only relatively easy characteristics, which are called frequencies, absolute or relative frequencies. And graphical approaches, there are some pie charts, or we call some different kind of plots, like for example stacked bar plots and so on. But pie charts are relatively easy, could be done in Microsoft Excel. To be honest, in scientific papers, there are absolutely no pie chart, because pie charts is something which is a typical plot, which is unfortunately very commonly used by some politicians and so many people in TV and other kind of events like this, and some, let's say for example, some campaigns before some elections and so on. And typically pie charts are used to, for example, distort the reality a bit, because the problem is with pie chart. There's an example of pie chart, for example, here. The problem with pie chart is that we as humans typically we are not able simply to, for example, distinguish between small angle differences. If I would simply say to you that this part of the round, like this one, there, like, for example, there will be, for example, let's say 60 degrees. If I would tell you that there is 62 degrees here, and there is, for example, 59 degrees here, definitely we are not able to confirm it or just to reject it. Absolutely hard to realize if this is true or not. But on the other hand, if I just write down or just draw two segments, one segment would have 62, for example, centimeters, and the second one would have 59 centimeters. And we will just put them pretty close one to each other, parallel to get them parallel. Then it's pretty easy for us to tell that one is longer than the second one, because if we have two parallel segments like with different lengths, it's easy to us to tell that one is longer than the other one. But if we have these two like parts of rounds, it's relatively hard to say for us to tell if these two angles are equal, or they should be equal because the percentage is equal. But if there will be no information about percentage, it will be pretty hard to say that if there is, for example, 60 or 60 or 69 or 65 maybe, or 55, 52, 56, 59, 61. Hard to say this, hard to decide this. So that's why pie charts are usually not used in scientific papers, because it's not so much natural for people, for us as humans to work with angular measures. What is easy for us is to use to work with linear measures, but not with angular measures. Yeah, so that's why pie charts are typically used as misleading plots, misleading charts in some, for example, pre-election campaigns and so on, because you can try to lie with pie charts about some, for example, some results, and so it's really easy to lie about the variables, about the some results using pie charts because of this fact. We are not able naturally to distinguish between the even for the A and 0 here. If there is maybe, I don't know, 120 degrees or 130, absolutely not possible to distinguish, and absolutely not possible to, for example, compare this white part of the round and this like the light green here. Absolutely possible to tell if the number of degrees here and here are the same or not. So, so pie charts, we are going to talk about them, but the message is that in scientific papers, they are usually not used. So a frequency, what is a frequency? We distinguish between absolute frequency and relative frequency. Absolute frequency of a category, of a given category, because we are not now talking about qualitative variables, so categorical variables. So for a given category, it's equal to number of all observations with the value of category K. That's absolute frequency. I'm just going to explain it using an example. And relative frequency is a category of category K. It's a proportion of the absolute frequency for the category K and a sample size. So example, I think the example will be much more clear here. So if we are about to find the absolute and relative frequency of blood type A, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 people, 12 individuals in my sample. And we are interested in blood type A. So there is one guy with blood type A, there's another one here, and the last one here. So 4 guys here, 4 individuals in my sample have blood type A. So absolute frequency is simply equal to 4. It's as easy as this. Absolute frequency is just the absolute value. So I'm just about to count them up, and what I'm going to count up is a value of absolute frequency. So one more time, 1, 2, 3, 4. 4 guys, 4 individuals in my sample with a blood type A. So just the absolute frequency of blood type A in my sample is 4, because there are 4 individuals in my sample with this category of blood type. And similarly to relative frequency, if I already know what is its absolute frequency, so absolute frequency of blood type A is equal to 4, it's easy just to calculate this fraction. In its numerator, it's just this absolute frequency. It's written also here. It's just a proportion of absolute frequency and sample size. So sample size is 12. So there are 12 individuals in my sample. And absolute frequency for blood type A is 4. So 4 over 12 is 1/3. So relative frequency of blood type A in my sample is 1/3. It's as easy as this. It's really easy. So this is the way. So this is the typical statistics we use for description of qualitative variables. And pie chart is if I would just calculate both absolute and relative frequency for other blood types, like not only blood type A, but also blood type B and 0 and AB, then I'll just realize what are the fractions. Typically, the relative frequencies are more suitable to be used for creation of building up of a pie chart, because 1/3 is like I have to calculate 1/3 by it was like A, yeah, and 1/3 of 360 degrees, which is like the whole round, by 1/3. So 360 degrees divided by 3 is 120. So this central angle for the white part, which stands for a category of blood type A, should be 120 degrees, because it's 1/3 of 360 degrees. So that's it. And similarly, for the same for blood type 0. There's 1, 2, 3, and 4. Yeah, 4 guys, 4 individuals for blood type 0. So still the 120 degrees here too. And for B and AB, there are, as far as I guess, only 2 guys, B here and B here, and AB also 2 times. So their absolute values are 2 and relative values are 2 or 12. So just 1/6. Yeah, 1/6. So that's like 360 divided by 6 is 60 degrees here. Yeah, looks like this. And the percentage is a bit around it. Yeah. So pie chart is something which is handy, but yeah, not so much, not so frequently used in a scientific paper. But in some usual report or some, let's say, media, like normal media for like people which are not like scientists. So for example, some normal media like social media or some newspapers and so on, some magazines and so on. Yeah, why not? You can definitely use them, pie charts them. Why not? Okay, guys. So I don't want to continue maybe for now because contrary to my prior expectations, I think that it took a bit longer to give you this kind of talk. So I will continue with the infrastructure statistics in the beginning of the next lecture, which will be next Monday, so in 1 week. And then we will just like continue with evidence-based medicine. Yeah? So I believe that we can do it this way. Or what are your suggestions? I suggest to finish the lecture at this moment and maybe to continue with infrastructure statistics for the next week. I'm able to do it now, yeah, but I think it took maybe 40 more minutes. So I'm not sure if this is like the good idea to continue with this at this moment. So what is your idea? What are your suggestions? Yeah, Amethyst, I just noticed that you unmute yourself, so maybe you wanted to tell something. Can you hear me? I cannot hear you now. I'm sorry. Maybe there's a problem. I don't know, but I cannot hear you now. I'm going to go to chat. So to do it, yeah. So I'm checking the chat, but there's no in the chat, nothing in chat.
Sorry, Professor, can you hear me now?
Yeah, I can hear you, and I can hear you now. Lovely. Okay.
Oh, okay. Sorry, I think it was a problem with my device. I
Yeah,
think it's
no
better if
worries.
we continue next time, if you don't mind.
Absolutely, I agree with you. I think that it will be
Yeah, it would be really like it next time would be really good because now we're having classes since 8 in the morning.
yeah. Absolutely. Yeah, I think it's not a good idea to have longer lessons than 2 hours. Yeah, absolutely. And
Yeah.
now we're just touching the limit of 2 hours. So absolutely agree with you. And also the infrastructure is a bit more complex. So definitely we better to start with the infrastructure for next time. So next Monday. Okay. So
Thank
thank
you
you very
so
much for
much.
thank you too for your attention. Thank you for
Thank
being
you so
Thank
much.
you,
participating.
Professor.
Thank you. If you have any question, feel free to ask me now, or you can also email me or ask in chat, whatever you want to, and I will. I will continue in versus six next time. And if there are any questions at this moment, feel free to start shooting. Not literally. Eh?
Thank you so much.
Thank
Mm.
you. Thank you, doctor.
Thank you too.
Have a good day.
Yeah.
Have a nice day. Have a nice day.
Thank you. Bye.
Thank you. Bye bye.
Goodbye.